Hello and welcome to Vitosh Academy. Today we will be talking about perfect hash and generally how to implement it, and it would be interesting, I hope. So, what exactly are we going to be implementing? We're going to be implementing the idea about perfect hash that is from this paper here from the University of California, San Diego, and it is described from Michael Friedman and Andre Zemerdi. So what I like is first, it's probably tough to read, so I'm just going to read it once and explain. So it is a data structure for representing a set of n items from the universe of m items, which uses space n plus on and accommodates membership queries in constant time. Both the data structure and the query algorithm are easy to implement. And I think this paper is from long time ago, from 1984, probably a long time before anyone was born. But let's take a look and see what are we going to implement. First, what exactly is hashing? So this is pretty much the example that we have. Imagine a library with finite books, but only 10 shelves, or infinite books, but only 10 shelves. And we need just a way to put these books into the 10 shelves. And the return of the hash function is going to tell us on which shelf between 0 and 9 to put them on. So pretty much we have these integers here, and it's going to return you 4, 9, or 2. And it's going to be really quickly instant access. So what do? Pretty much we take 104 and we say our table size is 10, and it goes into shelf number 4. And where would this one go? Shelf number 9, and 42 should go into shelf number 2. That's great. The problem is that 52 would also go into shelf number 2, and 62 or 72 would also go into shelf number 10. Let's make it a function, simplest hash, and we'll simply have a number and then table size, because this is what we pass, and we're going to return the number by the table size. Easy as this one. So our data is, let's say, 15, 25, 35, and the ones from above, 42, 104, 599. Table size, well, it should be len of data. And let's see what is going to happen. Shelf equals simple hash and x table size. And we're going to print something so it's visible and understandable. This notation is actually fancy. Number, then the x inside goes to shelf, and here we simply write shelf, the return of this function here. So in this case, our table size would be 6. So let's see whether we would have collision. Yeah, we would have collision on 1, on 0, on 4, again on 0, so twice on 0, and on 1. So we would see that number 15 goes to 1, and the same for number 599. Well, it somehow works. I would say definitely. I would call this one as working, as far as we only have 6. The good thing is it's really easy to calculate. It always returns the same number. So you always look for book 15. It's always on shelf 1. The problem is somewhere else. The problem is that, if the numbers go higher and higher, we would have more and more books ending on the same shelf, and there we would be rechecking the shelf once again. And this is the tough thing. So the idea is, what can we do in general to improve our case? How can we make sure that we always have, let's say, shelves as many as our data, or similar, but we only have one book on a shelf? And can we be sure about it? Okay, before going there, let's make another simple hash, which is not the simplest hash. And we have number and table size, and explain what we would be having. Okay, first we would be having like k, and k would be given 5. K is our magic k, magical constant. Just explaining, okay, and it would be 7, so 7 is okay. Then the hash would be itself number times 7, and this is important because you see, for example, 15, 25, and 35, they are with the same step, but if we use number times 7, we are somehow lucky, and they would be spread between them. Then this one, modulo of the highest prime number after 599, our longest number from the data. I have a list of prime numbers from Wikipedia, so it's 599, 601 is the next one. So 601, and then we of course have a table size. So let's see what's happening here. Okay, and I'm going to try the same with this simple hash, and this one was the simplest hash. Okay, so, and again we are having like collisions 1 and 5, but the good thing is that here we can increase 8, for example. Let's see whether we would have collisions. Let me see. Simple hash 8, simple hash 8. Let's use 17. Why is it not changing? Strange. At least for 17, I was hoping to see something interesting. So 19. Yeah, I know why. It's about this one. So yeah. What about 11? Mm, 12. Okay, you see, like with this magic k, whenever we change it, every time it is changing, and sometime for sure with so many numbers we would be having like a case where we don't have collision. However, this is really tough to see. Like probably if we remove this and we only have 4 numbers, yeah, somewhere there would be a case. Yeah, let me calculate and find. And so with 25, we see that we don't have collision. However, the more it goes, the worse it happens. And we really do not have all the time in the world just to check what our magic k should be here. Especially the number, whenever they go higher, it's really tough. Just a question, what will happen if table size is actually not doubled, but squared? Would it be tough? Let's see. Which k are we going to use? We're going to use k1. was something like this, okay. Yeah, no, with such a big number of table size, we are actually quite happy. The thing is that we cannot have it squared here. So what happens? What should we do actually? Now the answer is that we should only have table size squared for numbers and positions which are on the same bucket, so to say, or the same shelf. Whenever I say shelf, think of a bucket and vice versa, like whatever is easier in your head. So let's continue and explain what we are going to do, how this algorithm is going to work. Okay. So we continue slowly, just stating the problem once again. So with this kind of hash, let's say all the books with IDs 15, 25, and 35 will end up on shelf 5. And this is called collision. And if we just pile them up in a list, finding a specific number becomes really slow with ON notation. So if we want to get a true O1 notation speed, we need a smarter ways to organize these shelves. And here then comes our beloved article, which is actually a bit low quality, but I mean low quality of printing, the one I found it, but it's okay. Probably 1984, someone had to make a picture of it back then. Doesn't matter. I hope you like the quality of this one. So we're going to implement the solution from there, and it is FKS perfect hashing. So it is a two-level approach. Level 1, we do pretty much what we did here with this simple hash, with magic K, or just K, or K prim, as it is mentioned in the article. And K prim is going to be changed. I'm going to show you how it changes. And then here we're going to use the biggest prime number, biggest than the biggest number in our data set. So in order to do this, we need to import random and unit test and define a helping function saying is prime, which takes a number and answers a bool and answers whether it's a prime. Okay, so if number is less than 2, return false. Yeah, 1, it is questionable whether it's a prime or not. We'll consider it not a prime. And for the negatives, it should not be working in our case, so it's okay. So for I in range 2, just to the integer number to the power of 0.5, or with other words, square root, and then adding +1. So let's see if number divided by modulo division by I is 0, then return false. Else, at the end, return true. I'm just going to show you why I'm printing. We are working only up to square root +1. Yeah. What doesn't it like? Yeah, like that. Okay, so is prime 101. Num is not defined. I'm just saying okay. True. I'm going to, yeah. And what about 100? It found it on I. Yeah. The idea is that it, for example, here, before returning, it only goes up to 10. and in our case probably up to 11, no, up to 10. The thing is that after 10, after a square root, it doesn't matter. There is no need to go higher, because if we go up, for example, 12, already 12, if it was existing as a prime, it should be by something that was smaller than 12. So, for example, there is nothing higher than 10 that wouldn't be caught if 101 was not a prime number. I hope you understand this idea. If not, for example, write all the divisions of 100 and see that there is nothing higher than 10. For example, there is something higher like 50, for example, but the answer is 2, and if we have 2, we would already be having 2 before 10, so we would have caught this type of division, 100 divided by 50 up to 2. So back to the point, that's why we only check up to a square root plus 1. Okay, I hope this is understood. And let's see the next prime. This is a bit more fun. Okay, I'll make here like int and be returning an int, and there will be a candidate n plus 1, and here we simply say while it is not is prime. Let me make sure I'm not printing anymore. Is prime candidate plus equal 1 and return candidate. There is always a bigger prime number, but let's see. Next prime after 101, it found 103, and the next prime after 103 would be 107, and the next prime after 107 would be 109, and the next one, and so on. If you have the nerves, you can find a lot of prime numbers this way. Anyway, so let's start building our FKS perfect hashing. So what do? We do a class, we make a class. And in the class, the first thing we do is the init function, which actually takes the list of integers init, and it sets them to list of elements. Why we use set here? Because we only actually deal with unique elements, with unique numbers, and our function is deterministic. So if we are having the same numbers 5 times, for example, in the same set, it would always be returning the same result and the same hash for each one of them. Yes, so self n should be len of self.elements. That's the idea. We don't do square here because it's easy with square, but we don't want to be that slow. It's kind of slow for bigger numbers. So if we have like a hash of, let's say 1000, it would be 1000 squared, which is a big number just for memory, which is not going to be used. Okay. So handling this case, if we don't have like an empty input, so self p equals 1, self bucket equals this one, and self level 2 tables equals empty list as well. And I remove this so it's not highlighted in black, and then return is okay. Now let's choose the number p. which is pretty much max value, and it would be max of self elements, and then the self.p would be next prime of max value. Fair enough. And I want to say so, put something like print info. It's just a variable that I like, giving me some information. I'm going to switch it on and off depending on whether I want to see it. I'll simply show you how to do it right now. No A here. Simply print info equals true. Yeah. Ta-da. List is not defined. Yeah, fair enough. Probably we should be using some import typing. Yeah. Here, import typing from typing import list optional and tuple. So now it should be okay. Okay, and what else? While we are coding, let's be doing something. Let's test in the same time. So our data here would be pretty much the same as in the article initially. If you remember the article here, it was giving an example with this M30, P31, and these numbers 2, 4, 5, 15, 18, and 30. So data would be the same, 2, 4, 5, 15, 18, and 30. And FKS would be just to see what's going to happen. So max value is 30, correct, and self P is 31. And if we put 31 here, it would give us, for example, I don't know, 37. Yeah, but let's stick with what we have. Okay, and we continue. How do we continue? We need to build the 2 levels of buckets. So self dot build level 1, and then self dot build level 2. This underscores means that this kind of functions can only be called from within the class, which is useful. Self build level 1, and we are referencing to the self as well because we need to use all this self P, self N, and all the other fancy stuff. So what do we do here? We attempt to find the multiplier k that distributes the elements into buckets. Okay. Let me remind you what exactly the whole function was about. I'll just put it somewhere here. So it's something like h of x equals hash equals this k times x. This is the k prime mod p mod n. And this is going to be markup. I'll remove the prim and I'll just put something like this. Fair enough. Or I can make it a bit better. Something like I'll stop and make it better. Something like this. Ta-da! This is our hash function. So let's continue with our first level bucket. Where were we? So while true, let's see what's going to happen. So self.kmain, which is this k here, we are looking for is random.rand integer between 1 and self p minus 1. So self buckets equals empty list for each one in range self.n. Quickly showing you what this does. For example, self buckets calling it this way, self n saying that we work with 100. Okay, obviously not ideal with 100. Not that 100 was the problem, but we see just gets like a list of 10 empty lists, as good as that. And here and finding our thing like that. Okay, so we do the hash function here for x in self elements. We need to find the index, which is pretty much the shelf in the previous example, if you remember. And it's like this, self kmain times x, pretty much every element in self elements, modulo by self.p, modulo by self buckets. No, self n. Okay. And having it like this is okay. Self.buckets index append x. Fair enough. And here we need some squares equals sum len bucket power of 2 for bucket in self buckets. And let's quickly explain what this does. Or should I calculate it? Let's say some square. Okay, self buckets. Let's say self buckets is something like this. And for example, here we have a lot in the same bucket, and then here we have this. And then this, and then some squares. You can stop the video and think what should be the answer here. I say that it should be 1, 2, 3, 4, 5 squared, because this is a squaring. So 25, 26, 27, 28. Let me know whether you think the same. So 25, 26, 27, 28. Yep, I guessed correctly. So some squares. And the thing is that we have a limit, and we are okay to continue if the sum squares is not bigger than 3 times length of self n. So in our case here with 28, based on 3, 4, 5, 6, 7, 8. 8 times 3 is 24. No, we wouldn't be okay to continue with 28. So here I'll use print info again, and we'll be printing step 1, and I'm going to be giving the sum of squares. Of course, like this. Then I'm going to be giving the n. This time I'm going to say self n because I'm going to say it. And then kmain self k-main. And then the most important part, I'm going to be giving the self buckets. And I need some kind of stuff here. Yeah. And if everything is okay, of course, I need to break here. Let's see. Didn't like something. What it didn't like? If print info, print buckets, break, outside of loop. It's not outside of loop. It is inside the loop. While to. Okay, in this case, first you need to know is Control-Shift-L. Control-L, no. Was it Shift-L? Yes. So just to verify 34, what it didn't like. Okay, some squares. Okay, main, self bucket, print info. If some squares. What about this one? Yeah, everything looks okay. Oh yeah, now I see while true, like this. It should be tap, and then tap. And then the break comes if it passes the if. Let's see, okay. And so buckets is not defined, okay. What exactly is our problem? That's a good one. So we have self buckets here on the while true. Then we have the elements, perfect, the square. And okay, print info, I'm just going to write it like this. Self buckets. Oh yeah, I know what's the problem. Self buckets should be self.buckets. Yeah, and we're almost there. This one doesn't have attribute build level 2, which is fair enough. We would make one. Okay. And that's the important thing. What do we see now? What do we see now? First of all, we see that our code is working, which is hopefully good. The max value is 30, correct. The self p, the next biggest prime number is 31. So the n is 6, correct. K main is taken randomly as 8. And we have 1, 2, 3, 4, 5, 6, 7, 8. We count this as 2, as 4 because it's a square. Let's see. Every time we do it, we see that there are like 2 in the same bucket. And this is exactly what causes our problems here. We see that K main is actually 21, but n is 6 because we have 1, 2, 3, 4, 5, 6, 7, 8. It's 12, the total count. So it's like 4 here, 8, and another 4 here, and that's kind of a big one, so 12. And still it accepted it because 12 is less than 3 times 6. Yeah, with smaller number, we can do a lot of stuff. You see that almost every time we have like 2 values in the same bucket, we even have 3 here. So it's 9, 10, 11, 12. This one I counted as a square. Okay, let's continue with level 2 and hopefully start making some more sense. So self level 2 tables. I'm going to be careful what I write here. And the answer is none times self n. What is this? Pretty much none times 5 returns 5 times none. And now let's need a loop. And pretty much we say our bucket size would be the length of the bucket. Like for example, here it would be 2. And the bucket size would be bucket size times bucket size, but this is for later. So if bucket size equals 0, like in this case, self level 2 tables with the position I should be looking like this: 0, 0, none. Fair enough, but this is not always happening. So mj equals bucket size times bucket size. Fair enough. And now while true, we implement a new k-prim. The thing with k-prim is that for every bucket within a bucket, it's a different k-prim. And it's random between randit with 1 and self p minus 1. But it's pretty much the same as the one here. Where was the previous one? Yeah, here. K-prim and k-main. Okay. K-main is the same for the whole bucket level 1, but for bucket level 2 we have for each bucket a separate one. Okay, now continue. While true, we need to find a way to put the buckets. So temporary storage none times mj. What was mj? mj was the squared size. So it's 4 here, and if we had 3, it should be 9. Fair enough. And then we simply say, did we find a collision? The answer is false, of course, because this is just, we just entered. And now let's say for x in bucket, the index is k-prim times x, pretty much that formula here. We are rewriting it again, modulo self p. And then modulo mj. Yep. Which works. It's good to have always something to calculate around. I'll leave these ones here so you can probably use them. Oh, we don't have we didn't write an exit for this one, so it's always for the while true. Breaking it abruptly and quickly restarting everything. Okay. Yeah, I'm not going to run it once more because I don't have a return and it's obviously going to break somewhere, unless I don't put a break here. Yeah. I hope you're still following with me. So for x in bucket, do the magic into the while true. This is where we are in level 2. So if temp storage index is not none, then it means that we have already someone there and we have a collision. And on level 2, we are not allowed to have a collision, so we say collision found is true and we break, and that's enough. Otherwise, temp storage index equals x. Fair enough. When we are happy, we go back to the same level as this one. If not collision found, no collision found is pretty much a success. We found a perfect configuration for bucket number level 2. And we need to record this one, so it's self level 2 tables. I is like this, keyprim. This is the one I was thinking about. Let me see. Pretty sure this was just keyprim. Then mj, the square, and temp storage. And of course we need print info here as well. It's gonna be a bit different. So step 2. Self, what do we need for step 2 here? Self to label. This one should be enough. Yeah. And then we break. And of course something is wrong. But fortunately I know what it is. Let's see. And this is what's happening. This is the interesting part. So for step 1, everything was perfect until we didn't put like 3 in the same bucket, but we were okay with it because the value was 12 and 6 by 3 is 18 and we are within 3 times. So step 2 here, it first, where was it? It first printed the first one, which was okay. Then it started printing the second one. It put 19 alone, 13 alone, 19 alone, 13 alone. Actually, yeah. And then 5 alone. Or actually not, I mean, let's see. So for 19 and for 0, okay, it put 30 alone, it put 18 alone. And then here on the big one, 4, 5, 15, it redistributed them like this. And yeah, 0 is actually for the fact that we have like empty, 1 is for the empty, and this one here is the corresponding k-main for level 2, k', so to say, sorry. Yeah, k'. So k' 19, k' 13, k' 5, and here for the big party, what happened was that we actually put like 9 elements, 9 buckets in the second bucket, 9 slots, so to say. And in these 9 slots, we easily found these ones here. I mean, it was probably quite an easy one. And everything looks okay, everything is perfect. We should be happy, I guess. Query. And the query, we give an x, which is an int, and we return a bool, pretty much whether it was found or not. And we are not going to lie, so we're going to check how we check it. Return false. So if the idea is that if we don't have any elements, we don't find anything. Absolutely makes sense. So now level 1, find the bucket. So index 1 is actually this one, self.kmain times x. I think I'm writing this one for like 4th time today or something, at least. Self p and then self n. And after level 1, we go to level 2. And I'm going to use retrieve level 2 parameters for that bucket. How do we do it? So if print info, of course, then print index 1, it's interesting, and then print f from query in, okay, then self dot level 2 tables are actually self level 2 tables. Would this bring us some information? Well, I'll say so. Yeah. I'll put something like here times 12. Just to show you what it is. What if we do it without this? Yeah, better. Okay, so the params are working or not. I haven't set them. Okay, so we get the params. This is called unzipping self level 2 tables index 1. This is the unzipping kprim mj, and storage equals params. We could have simply removed this, but this one is more understandable. So if print info, and if print info is actually print, if, okay, and here we say kprim is kprim, we use this, then numbers in that bucket, or better in English would be slots in that bucket, and then storage, it should be pretty much storage. Okay, now if storage is none, then I want to throw an error. Was somewhere here where I threw an error or not. Raise exception error. No, not like this. Something like this. Raise exception error. Yeah. If storage is none, raise exception, and here something useful. Error on value x. Well, it shouldn't be happening, but that's why we have errors, we raise exceptions, and it's good. It should not be happening in the general case. In our case, it happens sometimes. And finally, let's do that lookup. So index 2. Probably writing this for, I don't know, 5th time or something. And at the end, we do not return the value because we don't need to return it. We simply say it's true or false. It's better for testing this way. Let's see what we got. Okay, we decided to work with this once again. We put a maximum value of 30, self-pit 31. We made the first level here, and we have 2 and 4 in the same bucket, which actually makes our n, our value up to 1, 2, 3, 4 plus 4, 8. And then at the end of the steps, we see that here, no, not here, here, we put 2 and 4 in the same second level bucket together, and we have like 2 empties. That's good. And let's see what will happen if we say FQS query, let's say 6, that doesn't exist. Into the division or modulo by 0. Yeah, it's interesting. The good thing is that we threw an error. Let's say with 5, it should only say true. And this is what happened. Probably it would make sense to simply return false. So it is testable. So with 6 we have a false, and with 5 we have a true. And this is from the query of self tables. Well, we see that somehow all the numbers in the second bucket were at the end, and a lot of nonce here. This is the K', and this is the size of the bucket. K', size of bucket, K', size of bucket. Yeah, fair enough. Now I know everyone else here is waiting for the tests, I guess. So let's start with the tests. Class test FKS algorithm. And it inherits from unit test case. And let's make a few tests. Test paper example. Self. And I'm not going to bore you with writing the tests. I'm going to write them without you watching the video. So just give me like a few seconds. And the tests are ready. Pretty much, let me show you what it looks like. We are testing pretty much everything. I just uncomment something assert false, but in general, we are testing the standard algorithm, then we are testing the algorithm with the jumps. We are testing like n between 1 and 1 million for range 30. Self-assert true, self-assert false. Everything looks perfect. Single element test and an empty test. We test it. I have uncommented this one as well. And we see that everything runs perfect. Absolutely running as expected. But is it true? The answer is no. We made somewhere a mistake. And this mistake is caught by the tests. Let me show you. We are asserting false on 3, 31, and 100 here. And we are asserting false on -1. I said we are asserting false, and it is like this. We have 2 errors. And there's something about division by 0. So my question is, do you know where the errors are and what caused them? Have you noticed while I was coding? Probably no, somewhere. The answer is somewhere on this screen. I will even zoom up a bit more and make it nice with Zen mode. And the answer is really, if you take a look and understand where was the big mistake, it's not a big mistake, it just doesn't work. It's interesting, the answer is here. We need to continue. The idea is if the B size is 0, we are perfect. We set it to this. And we go again to the loop. So it's a go-to, which is syntactic sugar. Continue is a syntactic sugar for go-to on row 31. And we need to ignore this part. Let's see. And we see that all our tests are perfect. Okay, already 37 minutes and counting, probably 38 on your screens because of the entry videos, or even more, I'm not sure. Let's make a quick recap and see what we did. We took a look roughly at this paper, an old one from 1984 for perfect hashing of numbers, where the function is actually, the hashing function is actually really simple. It is this one, hash of x equals k times x mod p mod n, where k is just a random number between 0 and whatever, mod p, or I mean, let me see whether it was, yeah, mod p is the next prime number after the biggest one in the set, and mod n is the number, is the length of our list which we are hashing. So we do this hashing into two buckets. Bucket 1 is this one, and if we have like collisions in bucket 1, we put a bucket 2 there and make sure that we do not have a collision because we square the size of the bucket. And with a squared size of the bucket, it is mathematically proven that at least every second time we would not be having a collision with k, which means that for a size of 25, if we try 12 times, if we try 13 times, for sure with different case, we would not have a collision. And having 12 times collision in a row is like 0.5 to the power of 12, which is a tiny number. Usually we only have like 1 or 2 collisions on the second way, on the second level, which means that if we have 2 collisions, we rebuild 2 times, but it doesn't happen a lot. Okay, so we did the perfect hash, back to the point, and we printed it and we tested it, and everything is okay in the tests. So far so good. Thank you for watching and staying with me in this large video. I hope you enjoyed it and I hope you learned something new. Enjoy the rest of your day. Goodbye.